Okay. So it is my name is Yoshikazu from University of Tokyo. It is my, let us start today's talk. It is my great honor to introduce Professor Glen Wheeler from University of Wollongong, Australia, Sydney. He received a PhD 2009 in Wollongong University from Wollongong University, and later he was working. He is working on. He's even since PhD study. He's studying higher order curvature flow, and he won the Humboldt Fellow in Germany, and and he's not only good in reading and research, but also he's good in presentation. He was awarded from Australian Math Society for excellent teaching 2018. He's currently working on University of Wollongong as a senior lecturer. Okay, today he's going to talk on current progress in higher order curvature flow. Please, Glen.
Thank you, Yoshi. Thank you for the introduction. Very nice. And thank you for the invitation to speak here. It's my great honor. I want to get started because I have a lot of things to get through. And so I start with this little comic. And this is Calvin, if you're unfamiliar with Calvin. And he's a little boy. And he's sitting at his desk, his school desk, thinking about schoolwork, and he says, "What on earth am I doing in here on this beautiful day? This is the only life I've got." And then he runs away. So to all the participants, I thank you very much for your time. I know that investing time and listening to a talk, you want some return on your investment, and I hope that this talk delivers something. Some kind of interest or some new knowledge or something like that. And for me, it's not often that I do a survey talk. For me, usually I give a talk on a theorem or a result or maybe a paper, something much more specific. And so I thought I'd start off with working out some terms of reference. So we go for a definition. A higher order curvature flow is an evolution equation for an immersion. So this would be a submanifold that involves 4 or more derivatives of the immersion. And this definition, it excludes many things, many beautiful things, really, because we don't have, for instance, the Calabi flow, flows of metrics are not included here. I'm thinking specifically of work by Piotr Kruszal, is not included here. So I won't, unfortunately, be talking about that. There are gradient flows of the Dirichlet energy for the Riemannian curvature tensor. I'm thinking specifically of work by Jeff Streets, and that won't be talked about here. And they are just beautiful papers. So I really encourage you, if you're interested, to look those up. Apart from flows of metrics, there are also flows of maps that I'm not talking about today. So these include biharmonic map heat flow, polyharmonic map heat flow. It would be really difficult for me to think of all the names that I'm not, of people whose work I'm not talking about here, but they would include people like Melanie Roopflin, Wang, Changyu Wang, Tobias Lam, Andreas Gastel, there's Parker, Christine Breiner, heaps, Paul Laurent, Tristan Riviere, Moser from Bath. There's heaps. There are so many, and I'm really sorry that I'm not able to talk about all of those works as well, because it's just too much. And in fact, I will mention flows that fit this definition, but really my main focus today is going to be on the surface diffusion flow, the Willmore flow, and Chen's flow. And I'll write down those evolution equations on the next slide in case you're not familiar with them. Surface diffusion and Willmore are natural choices, and Chen is a little bit of advertising, which I hope you will permit me to do. I didn't ask permission, but I'm hoping I have permission. Okay, now, but even within those categories, even within one of those, say even within surface diffusion or Willmore, the number of papers and the amount of research that's been produced is phenomenal. This is an extremely active field, and there's just a lot of work out there. So I found it necessary to further reduce the scope of this survey, which is submanifolds without boundary. So a lot of the time we're going to be talking about closed surfaces, closed curves, closed four manifolds, and usually in Euclidean space. I'm not going to be talking about boundary value problems, and that's really active right now, especially with just maybe a week or two ago, a survey by Alessandra Pluta, Novaga, Mantegazza maybe, came out on elastic flows of networks, which is a wonderful survey. I encourage everyone to take a look at that if you have the chance. So I won't be talking about networks or free boundary problems, problems supported on lines, things like that, or supported on planes. I won't be talking about any of that. I'm also not going to be talking about anisotropy. There's a lot of papers on anisotropic versions of these flows. Non-local flows where you have either non-locality in the functional, which, for example, you might see non-local mean curvature flow, but that's second order, or from a forcing term like volume constrained, Wilmore flow. These things exist. I won't be talking about those either. So I'm very sorry if you were looking forward to hearing about those things, and I'm not going to talk about them, but I had to make some tough calls. Even with, okay, so isotropic flows, even with this restriction, which might sound very restrictive, there's still quite a lot of work. And because I have a limited amount of time, I've decided to focus on things that, and this is my own personal bias. So I'm not trying to claim that I'm correct in this in any way. It's just my own personal opinion. It's like going to a museum and you're looking at the artworks and I think, okay, these are my favorite ones. It doesn't mean they're the best. I'm not an art critic in any way. But I try to focus on the general ideas of existence and uniqueness. So that will be focusing on regularity of so smoothing effects or the lack of smoothing effects, when you can generate a flow from what kind of data with what regularity class, what kind of topology, what kind of assumptions on the geometry, the principle of concentration compactness, blow up and finite time singularities, stability and convergence. Those are the things I want to focus on. So those are my terms of reference for this talk. And I've put issues here in bold because what I really want to do right now is focus on the issues with higher order curvature flow. What are the main problems in contrast to second order curvature flow? In general, there are always exceptions, but in general. But before I do that, I really should fulfill my promise of describing to you what these three flows are. Okay, so the first one is surface diffusion flow. And it's called surface diffusion flow because classically it was proposed in 2D, but these days it's studied in any dimension. Sometimes in one dimension it's called curved diffusion flow. Sometimes, I don't think I've seen it called the hypersurface diffusion flow, but I have seen it called surface diffusion flow even when it's in 1D or 10D. It's the same thing. Okay, so what is it? It's a H-1 gradient flow for the area functional. It was proposed in 1957, which makes it technically the oldest of these flows. And here's the evolution equation. So it's something like a biharmonic heat equation. F here is a one parameter family of immersions, and I've given this the number 1. And you can see this object here. G is the metric. Now, because this F is an isometric immersion, the metric here is just the pullback metric. And this little perpendicular symbol is for the normal Laplacian, the projection onto the normal bundle. And the H with the vector is the mean curvature vector. Okay, if you're in one codimension, it just looks like this. Okay. Now I've got this horizontal graphical here because recently we've been very, very specific in the notion of gradient flow with functionals. So I can't help myself but to put these two qualifying words here. But if you want to know more about that, it's a whole story, and I'm happy to talk to you about it. Maybe in the coffee break or something. Okay, the second one. This is the L2G gradient flow of the Wilmore energy, which is just the L2 norm squared of the mean curvature in 2D. It's classically a two-dimensional flow, just like the surface diffusion flow. But again, there are works in any dimension. And in fact, yeah, well, I'll talk more about challenges, but that is a challenge to go from 2 dimensions to other dimensions. It's somehow conformally invariant. It's not truly conformally invariant because if you invert the functional, so if you invert the surface at a point on the surface, then you may gain or lose energy, because if you invert a plane, then you get a sphere, and the sphere has positive energy and the plane has 0 energy. So sometimes when you invert, you gain or lose energy, but it's very well understood when that happens. Otherwise, it's a conformal invariant. And it was proposed, I'm not sure exactly when was the first reference to it, but I found some talks in the year 2000 where I think it was Ernst Kuwert gave a talk at ETH in 2000. And I don't know if it predates that, but that's the year I've put here, and they proposed it. So what does it look like? This is the Euler-Lagrange operator for the Wilmore energy. It has this quadratic term in the trace-free second fundamental form. This A0 is trace-free second fundamental form. And in one codimension, it simply looks like the norm squared. Okay, so what can you tell about this? It looks quite similar to surface diffusion flow, except for this cubic nonlinearity term, which ends up making a lot of difference. And in 2D, I will just say that it's critical in the Sobolev scale. That'll become important later. Okay, now the third one, which is my little bit of advertising, is this Chen's flow, which is called the Chen's flow because it has relation to B.Y. Chen's program for the spectral decomposition of submanifolds, in which you get this biharmonic operator appearing on the second term in the expansion. And this was proposed by us together with Jan Bernard. So this is Valentina and me and Jan Bernard in 2019. And it's simply the biharmonic heat flow of emotions. So you take exactly the Laplace-Beltrami operator and you apply it twice so that you get truly the biharmonic heat flow of emotions. If you write down what this means in one codimension and you don't write down the tangential part, so there is a tangential part that I haven't written down here, you can see that it's again critical for surfaces. It's got a cubic nonlinearity in the curvature, but there are two differences. The first difference is that this plus is a minus, and the other difference is that instead of the trace-free curvature squared, you now have the full curvature squared. Okay. Right, now I can finally talk about what I want to talk about, which is the issues and the challenges. Okay. So here's a fun fact. And this might not be this might be a rather negative slide because we're talking about issues, but that doesn't stop us from using the word positivity. And this fun fact is that higher order PDE do not preserve positivity in general. There are some exceptions. To mind the paper by Ben Andrews on the affine curvature flow of curves. You know, there's this notion of high degeneracy allows us to preserve some things, but in general, it's not preserved. And actually, a good description of this is in these papers down here. So I've tried to put little references throughout for papers that I think I will mention, but like I said, there are hundreds of papers. And so I may mention a paper that's not in the list here down the bottom, and these are just listing the authors and the year that it appears. So if you have any questions at all about bibliography or you want to find papers, just let me know. I'm very happy to share them. And if I've missed someone, just please tell me. I apologize in advance 1,000 times because I'm sure I'll miss people. But these papers, this Giga Ito, and Ito, these were really the first papers, as well as I think it's worth mentioning this Elliott Meyer Pape paper. This talks about non-preservation of graphicality. And Giga Ito here and here is about non-preservation of embeddedness, you know, and non-preservation of convexity. These are things that are true. It was really, okay, and so I'm just going to reveal all of these. It was really explained in great generality in this paper down here by Blatt, Simon Blatt, where he gave a very general class of higher order flows for which you don't have preservation of convexity and you don't have preservation of embeddedness. And it's not really hard to see why that's true. I'll talk about that on the next slide. But I just wanted to mention each of these things. So you don't have an avoidance principle, there's no comparison principle, which means that it's not going to be very easy, and we don't know how, to do viscosity solutions or level sets. It's without a very different notion of those things, probably not true. There's not really any kind of self-avoidance principle apart from some special cases, which I'll talk about later. There's no preservation of convexity or mean convexity or star-shapedness without some special hypothesis. Okay, and there's no preservation of graphicality, and we have pinch-off. All right, so that's a pretty negative slide about positivity preserving property. Oh, I should mention as well that this positivity preserving property terminology, I learned that from Hans-Christoph Grunau, who was my host in Germany during my Humboldt Fellowship. And a lot of the things that I learned about this come from him, so I have to give him some credit. Okay, now I'm going to challenge myself to draw a beautiful picture. You can be the judge of if I succeeded or not. Okay. So here we go. I'm going to try to use the Zoom annotation to do it, and you know, I'm not good at using it, so please forgive me if it's terrible. Okay, now what I'm trying to demonstrate here is the relationship between non-preservation of embeddedness and pinch-off. And I want to just quickly give an impression, and I don't have a clock actually, let me just, usually I look in the corner of the screen, but I've got my phone so I can, okay, keep an eye on the time. All right, so here we go. I'm going to try to draw a rotationally symmetric surface. I've used pink, which is, you know, a good color, this kind of thing. All right, anyway, that's my best attempt. This thing is supposed to be rotationally symmetric. And this is a neck. Okay, now this is a dumbbell. Put this on a, okay, so I'm going to call this pinch off, question mark. Well, how can we prove pinch off? Well, if this is a curve, imagine this is a curve. Now this idea is something that I saw in Giga and Ito's paper, so I think it's a fairly general idea. Imagine this is a curve. Okay, so if this is a curve and it's not rotated, then this kind of configuration is smooth. This is smooth in 1D for just a curve as an immersion, okay? It's not an embedding, but it's an immersion. And what you can do is you can zoom in on this point here, x0, and you can take a look at it. So we're taking a look at this point. Okay. And just let's look at the top part. All right. Now at this point, we have something which looks like a sort of a convex graph, like a quadratic. And what we can do is look at the evolution equation for the graph function at that point. And so what we'll find is something like ddt of u equals a function, let's just call it f of x0, and then it'll be multiplied by minus u, and then 1, 2, 3, 4 derivatives. Okay, and then plus, and then there's going to be a lot of lower order terms. Okay, now what we can do is we can choose this curve using the Taylor expansion such that this term is large. So we can make this large. Okay, and then what this is going to say is that this point, once we flow from here, this point should move downwards. And my picture is not living up to its expectations of being beautiful, but you know, it's all about it's all about effort. So this point will move in this southern direction, okay, with this given initial curve. And so then what's going to happen is these two leaves are going to cross. So what do we do now? We use continuous dependence on initial data, and we show using estimates that if this is initially separated by a small amount, there's an epsilon, then after waiting some short time, they will cross. And that's the idea of Giga and Ito's proof, as far as I understand it. And it's also the same idea that Simon Blatt used when he did his proof for the more general flows. Now, why doesn't that work over here? Pinch-off is a big problem in higher order curvature flow, and in particular, trying to show that it exists analytically is difficult in finite time. Now, what happens if you try to do the same thing here? Well, basically, you can do the same thing. You can take your picture like this, and you can write the flow for a graph function u. Okay, it's still going to be a scalar PDE. Rotational symmetry is preserved, so there's no problem with that. But the problem is that, so what's the problem with this approach, to this naive approach to trying to prove that pinch-off occurs in finite time? The problem is that we can't flow the pinched dumbbell. It's very singular. We can't flow it. So in particular, there's no continuous dependence on initial data result that we can use, and there's no way to, as far as I'm aware, to using this idea to prove the existence of finite time singularities. So we need a new idea. Okay, and that's my beautiful picture. So that's the connection. So you can see that while this will work very nicely around regular points to try to prove that self-intersections occur, because self-intersections are smooth, it's not going to give you the same kind of result when you don't have a smooth point. There are some exceptions to what I'm saying, but I think that's basically true. So I'm going to clear off all my graffiti, and I'm going to go back to my slides. Okay, the next fun fact, which is just as fun as the last one, is that higher order curvature flow and higher order PDE in general seem to behave mostly quite well. We just have a lot of trouble proving it, and we have a lot of trouble creating tools to prove that. So what are the big challenges? The big challenges are we need to prove that finite time singularities exist for natural configurations. So I should mention some previous work. There is work by Simon Blatt, that shows that for the Wilmore flow, and I'm going to talk more about his work later down the line, but essentially he proved that finite time, that infinite time singularities exist, and he gave some explicit examples. But it wasn't possible to show using that machinery that they occur in finite time. Now contrast that with your intuition and with the numerical work, in particular by Meyer and others, that demonstrates that singularities actually occur for these configurations very, very quickly. So So there you go. So that's a big problem. For surface diffusion, you also have the same problem. So that's for Wilmore. For surface diffusion, you have the same problem, and it's expected as well for Chen. Now, what we can prove, we can show that finite time singularities do occur. Now, why I've put natural configurations here is we can show that for some flows, like if you take the Helfrich flow of surfaces, the Helfrich flow is something like the Wilmore flow, so the Wilmore functional plus the area functional. And then sometimes you add on volume as well. So you take the L2 gradient flow of that, and you look at the resultant flow. We did that in 2016. And you can prove that singularities occur in finite time. So that's known. And Zimon extended that result recently in 2018 to deal with some more cases that we couldn't deal with. But that's not, what's happening there, what's behind that result is that the area functional and the volume functional, they are wanting to drive the surfaces to points. They wanted to bring the volume down. So really what's behind those results is that the higher order terms are perturbations. And that's a nice result, but it's not exactly proving the existence of finite time singularities for the surface diffusion or for the Wilmore flows, the vanilla kind. And I think that's a real challenge. Okay, and so this is my first reference to what I've called Giga's question, and Professor Giga can tell me if it's a question or a conjecture at the end of the talk. I'm going to talk more about it later. But we need more ways to classify singularities. Right now we have this very powerful concentration compactness machinery that was really introduced by Kubert and Schätzler in 2001, which is very, very powerful and very useful. But I think that by now we've really exploited it quite a lot, and we need new methods. We need new ways of classifying singularities. I should mention down here, because I have the references, Mantegazza in 02 and Eminenti Mantegazza in 03 and Bellatini Mantegazza Novaga in 04. This is a series of beautiful papers where they study a conjecture by De Giorgi. This is on the distance function, and they prove what they're trying to do is approximate the mean curvature flow by a singular perturbation that involves adding on higher order terms. And so to do that, you take the area functional and you add an epsilon times a gradient of the normal. And you can raise that to a high power, which is what happened later on in work by Fonseca and her collaborators. But you can also just keep taking more and more gradients of the normal. And that's what Mantegazza did. You can also change the functional slightly so that it lines up perfectly with what De Giorgi wanted, which is what Eminenti and Mantegazza did. And then you can prove that as you take epsilon to 0, you get convergence to the mean curvature flow, which is what Bellatini, Mantegazza, and Novaga did in 04. And the reason I mention these is that these regularized flows have no singularities. So these are flows of any order, as long as the number of gradients that you take of the normal is above a certain cutoff, which is determined by interpolation inequalities. It's a dimension-based cutoff. The flow has no singularities. It's not exactly a flow that has a particular name, but it does give you some good intuition for the kind of vocabulary that people use in terms of subcritical, critical, and supercritical flows. So all of these flows would be what we call subcritical. They enjoy beautiful regularity and convergence properties. Now, for flows that, and another flow that has that property, by the way, is the Wilmore flow in one dimension, which is also called the elastic flow. There are no singularities for that flow, but convergence is less straightforward, but there are no singularities. Okay. The third point I put here is special solutions. I think we need a lot more examples of special solutions. Right now for surface diffusion and Wilmore, we have stationary solutions. Surface diffusion flow is stationary on CMC hypersurfaces and more generally on parallel mean curvature hypersurfaces, submanifolds. And Wilmore is stationary on the Wilmore surfaces and Wilmore hypersurfaces, and those are well studied. And Chen is stationary on minimal hypersurfaces, but special solutions like shrinkers, translators, rotators, these have been hardly studied at all. It's a big open area, and I encourage everyone to go and look for them. We found that the lemniscate of Bernoulli, the very classical lemniscate of Bernoulli, there's an article in the AMS Monthly that has something like 60 applications of the lemniscate of Bernoulli, and this is number 61, and this was in 2016, and it's just a straightforward calculation that shows that this lemniscate of Bernoulli is it's a figure 8, and it shrinks self-similarly, and that's also true for Chen's flow, which is pretty surprising. Okay, and then the last thing that I want to say is that we need to understand stability in more ways, and you're going to see what I mean by that when I start to get into the specifics of what's known for these flows. But basically, we are looking kind of at perturbations of spheres, planes, in a certain topology, and the existing results are that these things either are stable or they're not stable, and that needs to be expanded. We need more of that, and we need more topologies. Okay, I want to just give a little bit more of a qualitative description of why this is difficult, and maybe a justification for why there isn't more work than what we're going to see. I'm just going to check on the time. Yeah, 3:30 past. Okay, so this picture I've taken from an article, it's figure 1 from the article of Castro and Guven, which is in the Physical Review journal. So this is a physics paper, and this is an inverted catenoid. So let me just write this here. This is an inverted catenoid. So we all know about catenoids, I hope. If we don't, then you have a lot of great things to learn, and I envy you because catenoids are beautiful things. Catenoid is this sort of surface of rotation, right? And it's a minimal surface. And there are two different catenoids. Anyway, there's families of them. Now, if you invert around the origin, this catenoid, then okay, let's just take this to be, say, the unit radius. Then these points are fixed points under the inversion, and infinity. This infinity is going to come down like this. So this infinity here has been pushed into the origin there, and this infinity over here has been pushed into the origin from this direction, and you end up with this kind of shape, which I'm doing my best to draw. Okay, and then you can see how you get this kind of thing. And there's this very interesting double point at the origin. So it's a double point. Okay, and then you might think, why, Glenn, why are you telling me this? Well, because inversion preserves Willmore. And in particular, the catenoid is a minimal surface, so this is a Willmore surface. This is Willmore. Okay, now I'm telling a little bit of a fib here. This is really branched Willmore. And that's a nod to the great work by Tristan Riviere and his collaborators, including Jan Bernard and Paul Leron and many people that have done a lot to analyze this, including Kuvert, Schätzler, and Lee, and everyone. But what Castro and Guven show in their paper, using very simple calculations, is that this point here is a curvature singularity. It looks like a nice point, right? But it's not. It's a curvature singularity. Okay, now keep in mind that the catenoid is smooth, okay? The catenoid has no singularities, but it's unbounded. So this is a curvature singularity, and the graph function u, if you wrote this locally as a graph, is of class, regularity class C1 alpha. Okay, so it's not C2. And the curvature, by the way, goes like minus the logarithm of the distance to the origin. So it's a very mild singularity, but it's a singularity. And you might ask, well, what about the Willmore flow? Is the Willmore flow stable? Because this is a compact, not very smooth, but compact surface, closed surface. Can we take the Willmore flow? And the answer is sort of, yes. So the Willmore flow of this, so let me just mention now these papers of Curvature and Schätzler. Curvature and Schätzler's breakthrough result is that if you have the Willmore energy of your initial immersion less than or equal to the Willmore energy of two spheres, then the flow converges smoothly to a sphere, to a round sphere. And the Willmore energy of two spheres is exactly the Willmore energy of the inverted catenoid. So this is actually also equal to the Willmore energy of the inverted catenoid. Isn't that nice? There's a slight wrinkle, which is that the Curvature and Schätzler's framework applied to smooth flows and not to C1 alpha flows. But you're going to see that we can combine results to get some kind of convergence statement for exactly this initial data. Problem is that it's not really stable. So if we perturb this configuration so that we reduce the Willmore energy below 8, so to 8 pi, so to the energy of two spheres, which is 8 pi. So if I accidentally say 8 pi, then that's two spheres. If we do that and we reduce the energy, then it definitely converges to a round sphere. If we increase the energy, which is also possible, then we don't know. And that seems very unsatisfactory, but that's true. All right. Now, the kicker, there's always a kicker. The kicker with this is that this is not the only catenoid. This is also from Castro and Guman's paper. And okay, so this little box here is the profile revolution for the inverted catenoid. And then if you take different conformal images, you get different profiles. And what are they tending towards? They're tending towards two spheres connected with a catenoidal neck. And they all have Willmore energy, two spheres, 8 pi. So all of that previous discussion, which seemed very reasonable when you had the deflated discocyte type blood cell sphere thing, carries over to this setting. Now, the difference intuitively, of course, is that this little catenoidal neck down here, you really think that this catenoidal neck should pinch off. All of your intuition from mean curvature flow, from everything, tells you that this should really pinch off because the flow should go to two spheres. It should go to a double sphere. But it, like I said, the same thing I said before is true here. If you do a small perturbation such that the energy just dips below 8 pi, then it will actually unfold and flow to a sphere. And that's amazing. But that's the power of Curvature and Schätzler's result. Now, the issue is that if you perturb a little bit bigger than 8 pi, we don't know. We don't know that it's singular. If we knew that it was singular, that would be a huge breakthrough, but we don't know. We just can't guarantee that it converges. Okay, and now I mentioned these other papers down here. There's Gonzalez, Massari Tamanini, and Gruder, and Morgan, and Rosales, and Wikram Sequeiros, and Bellatini, because these are on the CMC hypersurfaces, and I just mention them because a similar discussion can be held for surface diffusion. So this is a Willmore surface, but CMC hypersurfaces have a similar kind of property. The issue with that discussion is that it's much more limited because we don't have an analog of the Curvature-Schätzler type theorem, which is a big challenge. Okay. So I've spent the whole talk so far talking about what we can't do and what we need to do. And now I'd like to just talk about what we can do. Something positive and uplifting. Okay, we'll start with the surface diffusion flow. Now I'm going to start talking about specifics, and I'm mindful of the time. How many minutes do I have, Yoshi?
I think you have. I think you have 5 minutes.
5 minutes. Okay, so what I'm going to do is just really quickly go through these things. I'm sorry I won't be able to go through much detail, and then I'll just get to the last little slide. So we have this extremely beautiful paper by Escher and Muha that uses maximal regularity in Besov spaces to get existence. Koch and Lum did it in 09 for small Lipschitz constant. And there's minimizing movements by Fonseca and this all-star team of brilliant mathematicians who show that you can do it for W2P graphs, P greater than 2. And there's Leckrone, Shao, and Simonet that used Aman's theory, a development of that to show it for C1 alpha. Now, that C1 alpha is important when you think back to the inverted catenoid. Concentration compactness is shown as well for surface diffusion. That was about 10 years ago. And that says that if you have a singularity, then it can only occur when a certain quantum of the curvature concentrates. And this was first shown for the Wilmore flow by Kubert and Schätzler. And then I did surface diffusion flow about 10 years ago in 2D. And then in 1 year ago, together with Jan Bernard and Valentina, we showed that there was a whole class of flows that this holds for in 2D and in 4D, but not with exactly this functional in 4 dimensions. You need to add a gradient. So that gives you a classification of singularities in 2D and 4D. But the classification is useful, but it could be a lot better. What's known for blow up? The lemniscate of Bernoulli blows up in finite time. It's a shrinker. That was in 2016. Leckrone and Simonet studied axial stability and instability for different types of perturbations. That's for cylinders. Something like that isn't known yet for compact surfaces. And then what about convergence? Well, the Lipschitz neighborhood of planes by Koch and Lum. I did a W22 type neighborhood of spheres. Escher Muha have the Besov neighborhood, which is better in low dimensions, but worse in high dimensions. And Leckrone, Shao, and Simonet did something like C1 alpha in 19. So you can see there's continual improvement. And I've only included results that are sort of on the edge of what's best known. So in particular, for a lot of these, there's a lot of stuff before that I haven't included. And very recently, Miura and Okabe showed that, and this is the only result that holds, by the way, for immersions. It's a truly an immersion result, which is really important. They showed that if you have a immersed curve with many leaves, then if you take a certain type of symmetric perturbation, it flows to a circle. And that's a very recent paper. I'm going to skip forward to Giga's question and Cho's conjecture. This is Kai-Seng Cho, because I'm out of time. Wilmore flow, I've talked a little bit about Wilmore flow already, but this is the lightning speed description. I mentioned already Kubert and Schätzler's breakthrough papers, which shows that if the Wilmore energy is below 8 pi, it converges to or equal to a sphere, and that's only in R3 and sometimes with a different energy condition in R4. And Zimon-Blatt has classified blow-ups of rotationally symmetric Wilmore flows. There's an energy identity, and there's these examples that blow up in possibly infinite time that's not known. Lam and Nguyen in 15 extended this to include energy up to 16 pi, 4 times a sphere, where you add trinoids, Oedipus surfaces, and catenoids. There's convergence results, which are similar to the ones I showed, but in the Wilmore flow case, there's also convergence for tori, Mondino, Nguyen in 14 with this kind of topology, and a recent paper by Delacroix, Mueller, Schätzler, and Spenner in 2020 for rotational tori, and that's again below the energy of 2 spheres. Surface diffusion cannot have this result because numerical evidence shows that surface diffusion of a torus is always singular. Okay, now for Chen's flow, it's very recent, and I'm just going to skip it. If anyone's interested, we talk later. Now, I want to get to this because the chairman of this session is Professor Giga, and I met Professor Giga in, I think, 2013 at Hokkaido University, and we were at the Pacific Rim Conference, and he asked me a question. He asked me this question: if you have a curved diffusion flow, that has the property that it's an embedding for each t, must it exist for all time? And this is inspired, I believe, by numerical evidence that shows that all known singularities, even numerical ones from embedded data can be singular. They become first immersed. So they first lose embeddedness, then become singular. So really the question here can be rephrased as, can you get a singularity from a corner, from a cusp? Can you get a cusp singularity without the resolution of a loop? So the singularities that are known numerically involve the closing of a loop. And that should only happen if it loses embeddedness. And this is wide open. So Professor Giga can correct me on the date. I don't know when he first asked this question, but I put 13 because that's when I learned of it. Okay, and then the last thing that I wanted to highlight as a goal is again for curve diffusion. As you can see, a lot of things are very difficult in higher order curvature flows. So a lot of people focus on the simple cases and then generalize further. And that's definitely the case here. So this is from Cho's 2003 paper. And essentially it says that if you have a certain growth rate on the L2 norm of the curvature, then a parabolic rescaling should be self-similar. And this is not known to be true or false. We don't know. This is what happens for mean curvature flow. It would be a very natural thing to conjecture. And there are many results on this blow-up rate, but there's no kind of monotonicity formula yet that would allow us to kind of conclude this. And that's just a big open problem. And I'd love for it to be solved. Okay, I'm sorry I took too long in the beginning, but thank you for your attention.
Thank you very much. Thank you very much for your very inspiring talk. Are there any questions in the audience? In chat or raise a hand?
There are 20 chat messages.
20 chat messages. But no question?
Noah Kreitzman has permission to speak.
Sure. So, could you ask a question?
Oh no, I'm sorry.
No?
Yep.
Okay. Okay, I think time is too short. So, but I have a very basic questions. You mentioned three typical equations, and there are of course many common natures, but yes, many common natures. And what is the main tool or main tool to derive such kind of very beautiful results?
Yeah,
asymptotic analysis or finding good integral to control, or what kind of basic idea to
that's
study?
That's a great question.
To analyze these equations, finding good integral quantity, or
essentially
analysis.
Essentially, it's energy estimates. So so you take something like Sobolev norms that are localized, and you look at their evolution equations and you apply interpolation inequalities and things like the Gronwall inequality and control these norms locally along the evolution equation. So that's how you derive, so that very, very elementary technique, that's how you would derive the concentration compactness alternative. That's how you get interior estimates. That's how you prove existence of the rescalings of the blowups along with compactness theorems. And that's the main way you control the flow. There are other techniques though that I should also mention. So once you've done this, then you need to analyze the geometric structure of the blowup, and that's usually done with geometric rigidity type estimates. That can be done with a similar method or with a completely different method. So you can compare those to Liouville type theorems for higher order PDE. Now, apart from these energy estimates that are somehow elementary but can get quite involved, the other main techniques are, especially for existence, you have maximal LP regularity. and the sort of classical minimizing movements method that's been used as well. And then there are a number of other novel techniques. So if you look at the paper by Muha and Escher, this is maximal regularity. This is very harmonic analysis, but they use a number of novel methods in that paper. It's a brilliant paper, and they have to extend in various ways to treat surface diffusion. And these papers are remarkable because they work in any dimension. The energy estimates idea, we made that work in 2D and 4D, but it's not clear how you extend these energy estimates into other dimensions, especially odd dimensions. N equals 1 is okay because it's subcritical. But once you go to N equals 3, we're not really sure. Yeah, great question.
I see. Thank you very much. Are there any further questions? I also have another questions. Okay. What in one? Okay. Sometimes people discuss one dimension curve, and sometimes higher dimensions. What? Okay. Are there any big difference between one dimension and higher dimension?
Yeah, yeah, there are. So, for example, with each of these flows, there's big differences of each three of these. So I'll start with Wilmore. In one dimension, the Wilmore flow of curves, which I believe there are many papers on Linner's. I didn't cite him, but he definitely wrote a lot of papers. And there's Chuk, Kuvert, Chetzler, and then there are many other papers in addition to that. And the main message is that it's very easy to prove that in one dimension, the Wilmore flow is never singular. It's never singular. You can start with any curve and flow. And what the flow does is it expands the curve, makes it larger and larger, and turns it into an elastica. And you need to blow down, rescale it, fix the length, and then you will see a beautiful elastica. And that works in it works for a curve in any number of codimensions. So for a curve, a space curve, it's fine. And that's from Chuk, Kuvert, and Chetzler. Surface diffusion or curve diffusion, it seems very tricky. It's a very tricky flow. Sometimes there are singularities, like the figure 8 curve, the lemniscated Bernoulli shrinks self-similarly to a point. Other times there is stability. There are actually a lot of results. There's, I think Elliott and Garke wrote a paper more than 20 years ago on stability in W32, where you assume that the derivative of the curvature is small. And I wrote a paper in 2013 where you have a W22 type stability. But these other papers that came later are even better in terms of regularity. So circles are stable, but multiply covered circles, it's the Miura-Okabe result holds for symmetric perturbations of multiply covered circles. And that's it. But that's very different to higher dimensions, because in higher dimensions, say for surface, there's no known analog of the lemniscate. There's no known immersed surface that shrinks to a point. In fact, one of my main favorite questions for surface diffusion of a surface is for the Wente torus. So the Wente torus is a torus that is CMC and it's smooth. And so if you take the surface diffusion flow and you apply it to the Wente torus, it is stationary. And then the question is it stable in any sense? What about for smooth perturbations? Can we do some kind of center manifold on this? And it's unknown. And I think that's just a very fundamental question, because the Wente torus is a famous object. For Chen's flow, the main difference with these other two is that it's more like mean curvature flow, because it's trying to reduce the area as quickly as possible. It wants to make everything singular. So the problem there is to analyze the rescaling. where you fix the length.
Mhm.
And when you look at the rescaling, similar techniques fail. So this has been a very big challenge to do this Chen's flow, because the nonlinearity is such that a lot of the previous methods, the test functions that we use, the specific techniques, they don't work. So we had to use something different. And in fact, it's more similar to mean curvature flow than to surface diffusion. So whereas for 2D, so in higher dimensions, just because in higher dimensions, it was more like Willmore flow, and we could use the trace-free second fundamental form. So that kind of analysis worked quite well in 2D, but in 1D, it didn't work. So yeah, it does make a big difference.
Interesting. Okay, so I think in each problem, there's an important dimension for application. For example, surface diffusion flow, I think 2D and 3D are very important, right?
Yeah,
With
yeah,
a
absolutely.
higher dimension. How about Willmore flow? 1D is related to elastica, and 2D should be important. 3D,
Yeah.
I don't know, but maybe from the point of topology, maybe higher dimension also interesting. So
Yeah.
what is the typical dimension? The problem is very important.
Yeah, great question. So for surface diffusion, like you said, I think 2D, 3D is the most important for surface diffusion. I'm not aware of great applications in higher dimensions for surface diffusion. For Willmore flow, 2D and 1D, like you said, are the perfect realms for application. In higher dimensions, it's no longer conformally invariant. And so there are a few different choices for Willmore functional in higher dimensions, where maybe instead of taking an L2 norm of the mean curvature, you take an Ln norm of the mean curvature, or you can add extra terms. There's work of Rod Gover that classifies all conformal invariants with some conditions given dimension. And so the natural Willmore flows in higher dimensions may be these conformal invariants. And these conformal invariant flows are, of interest from the perspective of mathematical physics. Now, but for us, mathematically, this kind of evolution equation, it's important in any dimension because it's in higher dimensions, it should be worse, and we should be able to prove that intuition correct. So I feel like before we move on to more exotic types of Willmore flows in high dimensions, we should first show that this one already does not do the job. But in fact, it's just very hard to analyze in other dimensions. For Chen's flow, I really think this is more like a biharmonic heat flow, and it should enjoy a good L2 theory. And yeah, I think it should enjoy a good L2 theory. I think it's from its application point of view, for the spectral decomposition of immersions from B.Y. Chen, it's useful in any dimension.
Thank you very much. Okay, I think unfortunately time is now up, so I would like to thank speaker. Thank you very much, Glenn. Thank you. For wonderful talk. So thank you for participation. Okay. So long.
Should I stop sharing?
Stop
Oh,
sharing.
that's okay. Professor Giga, I will close the session.
Okay, thank you.
Okay.
Will you close the session?
All the attendees have received an invitation to the coffee break, so please join the coffee break.
Thank you.
Okay.